Properties of logarithms. So a couple properties we're going to talk about with logarithms here, and then what we can do to what's called expand or condense, which hopefully is a little familiar because we did this last year, right? Equality. So first of all, if you have the same base, you notice this is the same base of these guys right here, you can assume that these are the same number. All right, so if you have a log b of m equals log b of n, then you have to assume that those equal each other. And same with exponents. If you have a base to an exponent equals a base to the exponent and the bases are the same, then those equal. And this little IFF, if you remember from logic and geometry, means if and only if, okay, which means it works both directions. So this equals that if and only if this equals that, and vice versa. These two equal each other if those equal each other. So that's what that IFF, if you ever see that, by the way, it means if and only if, which means it has to work both directions for your if-then statements, if you remember that logic from geometry, okay? Let's look at the product, quotient, and power rule. This is what we use to what's called expand or condense, and it works both directions, okay? So, and I'm going to start on this side, actually, probably. These are the familiar ones. We actually know the rules for exponents, right? If you are multiplying like bases, what do you do with the exponents? Well, you add them, okay? We all know that. Well, the product rule says here, well, if I have a logarithm of a product, two things multiplied by each other, I can add them. Why does that work? Well, because of this rule right here. So I can split up my logarithm and I can say, well, the log of m plus the log of n, that's going to equal the log of m times n. Because remember, I'm talking about exponential. This is just the inverse of exponents, okay? So I can go the other direction. If I have a log that's split up like this and it's the same base, I can make it into one log and just multiply what was inside, all right? We know this rule, the division rule. If I am dividing like bases with exponents, what do I do with the exponents? Well, I subtract them, correct? Yes? Well, I can do the same thing with logs. If I have a log of something that is dividing, I can split up the log by subtraction. And the same rule applies going backwards. If I have two logs with the same base that are being subtracted, I can make them into one log and put them as division. And we're gonna practice this, and then we're gonna use it in solving equations, okay? And the last one we also know, if I have a power to a power, then I multiply those. And so if I have a power or an exponent on my log, I can pull it in front and multiply my log by that power. All right? Expansion and condense. So if it says expand, it's gonna give it to you over here like this, and it wants you to stretch it out. If it says condense, it's going to be like this, and it wants you to make it to one. The only way you can do this is if you have like bases. So you'll notice all of these have the same base, b and b, okay? Same base, and then you can do it, which is also true of exponents. The only way these exponential properties work is if you have the same bases. All right, so let's look at some of these examples. Expand each logarithm. They want us to split it up into as long as possible, really. All right, and so what I typically do with these is I do these a little at a time. The first thing I want to pay attention to is this is kind of like a group here, okay? So when you have a group, you need to pay attention to that, especially if it's in the denominator, because when you're subtracting, and if you had 2 in this denominator, you need to distribute that negative, okay? So pay attention to when your numerators have a group and when your denominators have a group. All right, so what I typically do is I would say, well, let's split this up a step at a time so you can see what we're doing. So the first thing I'm going to split up is this division. Remember, division is split up with subtraction. So this is the same thing as log. What is my base here, by the way? I don't see one, so my base is 10. All right, so I have something like this, right? And then I'm going to split up this first guy. This first guy is multiplication. So how can I split him up? So this can be split up with addition, right? So I have log a squared plus log b. And I am subtracting that denominator. And then I have one more thing I can do. I have some exponents that are here. My exponents can move to the front. So this exponent here can be in front of this log. This guy doesn't have an exponent. This exponent here can move in front. And that is as much as I can expand it. Okay, that's as much as I can expand it. The next one utilizes a root. Now remember, a root is just another form of an exponent, right? So anytime I have a root, I'm going to rewrite it as an exponent before I start expanding it. And so what's my base on this guy? Base E, right? When you see ln together, it's a natural E. It's a natural number E, base E. So I'm going to rewrite this. My numerator is 2c minus 1 to the 1/3. And that is over b squared. I haven't really started expanding yet. I just rewrote it. Okay? How do I split up that division? I split it up by what? Subtraction. So I'm going to say the natural log of the numerator minus the natural log of the denominator. Both of these have exponents. Now I cannot split up that binomial. I cannot split up the 2c minus 1. That whole thing is being taken the log of, okay? So you can't split that up at all. The only way you can split it up if we have multiplication or division, okay? We can't split up in addition or subtraction. That's a binomial. The whole thing is in that log, okay? But I can move this, these exponents out of the way. So this exponent can go in front. And I'm going to show you how they typically write this. Or sometimes they write it this way. Oh, did I say half? It should be a 3 there, by the way. Sorry. I'm writing and talking. So this is a 3. And this guy is also a 3. 1/3. And then minus my 2 ln of b. Sometimes you will see that 3 in the denominator. So you can say 1/3. I just want to show you this so if you see it and you need to condense it, this is another way they can write it. Sometimes they will write this guy as ln of 2c minus 1 over 3, right? That's the same thing as 1/3. Just so you know that that's a radical. That's a 1/3 in front. When you see the 3 on bottom, that's just like a 1/3 in front. And I will take it either way. You don't have to put it as a denominator. But sometimes when you're condensing, they will start out this way, and you need to recognize that that's just a 1/3 in front, which just means a root, okay? So for condensing, we're going to use these same rules for condensing. All right. Now, I will say that this one's a little bit different, this first one. You'll notice we have a 3 in front, and we still have something multiplied, which means they didn't expand all the way here. They could have expanded more, right? But this 3 exponent is going to go to this whole group, okay? It's going to go to everything in the log. Unlike the other one where we just had like an exponent on the individual ones. So the first thing I'm going to do when I'm condensing is I'm going to put those exponents into place. So this 3 is going to become the exponent of this group. This 1/2 is going to become the exponent of that. So I have log of this group to the 3rd power minus log of c to the 1/2, all right? And then I can do this subtraction. That's going to condense to division. So I'm going to say log, and the first one will be my numerator, and the second one will be my denominator. Now I can write that c to the 1/2 a different way, right? Any fractional exponent, that's going to be a radical. So I can write it one more time. Log of ab cubed over the square root of c. And if they wanted to, you can leave it like this, or sometimes they'll say a cubed, b cubed, but I don't require that. So in your book, they may actually have it like this: log of a cubed, b cubed over square root of c. Those are really the same thing. I don't consider one more condensed than the other, because condensed means you got it down to 1 log, okay? So as long as you have it down to 1 log, I don't care which way you write that. All right, so for the next one, the first group does not have an exponent. The second one does. So I'm going to combine my exponents first. This is going to be the exponent here. And then addition, well, that takes me back to multiplication. So I can say the natural log of b plus 1, b to the 5th, all right? You can leave it like this. I would actually probably put that b to the 5th in front just to make it prettier. Or you could actually distribute it in if you wanted to. These are the same things. So if you did this, that's the same thing, but either one is fine. Those are both considered condensed because you're down to 1 log. Right, so change of base formula. So you'll notice on your calculators you have a log and you have an ln. And yes, within your programming of your calculator, you can actually change your bases in your logs. But honestly, I really think change of base is easier. It's just as easy to just divide 2 logs than to go in and change the base in your programming calculator, which you can do for some calculators. Change of base is just easier. You can calculate any base using either your natural log base 8e, or your common log base 10. You can use either one. It doesn't matter which one. This will always work. The change of base formula says that as long as your base is not a 1, which you don't need a calculator if your base is 1, then this is going to work. I have some base other than 10 or e, okay? And I want to find out what the log is. And let's assume it's not an easy one, like log base 2 of 8. We all know that 2 to the 3rd power is 8. We don't need a calculator for that. But log base 2 of like 7, not as pretty, okay? And so what you can do is you can say, well, this is going to be another log, and we're going to use either our common log or our natural log of my number here that I was originally trying to solve for, divided by the log of my original base, okay? So let's look at this. They want log base 2 of 5.89. You are not going to do that in your head, okay? Nor is it a common log or a natural log. So what we're going to do is we're going to use a common log. And we're going to say, well, I'm just going to take log base 10 of 5.89, and I'm going to divide it by log base 10 of 2. All right? And when I do that, and they usually round to 4 decimal places, I get 25583. All right? And you can do that all in your calculator. Typically, when you do log, it's going to open a parentheses, close it, divide, log again of 2. So everybody try it on your calculator to make sure you know how to use your calculator to do change of base. And once you do that with your natural log. Natural log of 5.89 divided by natural log of 2. What do you get? Hopefully the same thing. Or you did it wrong. It works with any log. You could do log base 5 of 5.89 divided by log base 5 of 2. Not that that would be very practical, but any log, as long as you do it that way, it will work. So the log of the number you were trying to take the log of to begin with, divided by the log of your original base, will always be that answer. Which means, by the way, if in your calculator then you did 2 to the 2.5583, it should be approximately 5.89, because that's what you found. 2 to what power equals 5.89? All right, that's what you're asking when you're asking this. All right, and so you can always check your answers here, by the way, by taking your original base to the power of whatever you found when you did change a base. All right. Bach promoted the tuning of musical instruments so that the ratios of the frequencies of any two adjacent notes are constant. This method, known as equal or even temperament, causes the frequency to follow a logarithmic spiral. How crazy is that? The frequency of a note played by a key on the piano is related to the key's position on the keyboard. Obviously, even if you don't play the piano, you know that the notes change as you go up and down the keyboard, right? Frequency. What does frequency mean? What does frequency mean? When you think about musical notes, we don't really think about them being a wave. Any type of noise, right, is a wave. So you would have learned this somewhere in one of your sciences. Don't ask me which one. But it's actually, when you see it, it's actually graphed in a wave, okay? So when you see a note. And so when you have a higher frequency, it's going to bounce faster, all right? You're going to have your higher pitched notes, your basses, and you can kind of hear it when you hear somebody sing, right? It's going to be drawn out, right? And so it's a slower frequency there. It's a fewer, slower frequency going. All right, and so there is an actual relationship, which is why if you hear like middle C compared to one octave higher or one octave lower, you can definitely hear that it's the same note, right? The frequency has just changed, but it's changed specific to that note. Different than if you hear like a C compared to a G. Those aren't the same notes, right? So if you have a soprano singing a C and a bass singing a C, they're technically singing the same note, right? But they're singing it at different frequencies. Does that make sense? All right, and so the frequency of a note played by a key on the piano is related to the key's position on the keyboard. The number of notes in that one key is above another is modeled by a function. Number of keys you are away from it. N equals 12 log base 2 of F2 being the higher frequency over F1 being the lower frequency. All right, so the note C5 is one octave higher than middle C. By the way, all of your notes on your keyboard are actually numbered like this. Most people don't know this, but C5 is one octave higher than middle C, and it has twice its frequency. How many notes above middle C is C5, okay? And so you are going to set it up in here. All right, and so we're going to set it up in this formula right here. And we're going to say how many notes above. That's what we're actually trying to solve for. So we're going to leave that guy alone. All right, we're going to leave the 12 alone. We are going to say log base 2. It says twice its frequency. So we do not know the frequency of middle C, but we do know that C5 is twice the frequency of middle C. All right, does everybody see why I did that? What can happen here? My same rules apply. What happens to that F1? I have F1 on top and F1 on bottom, right? It cancels, all right? 12 log base 2 of 2. Do I even need a calculator here? What is log base 2 of 2? 1. Base, and when base and what you're finding is saying 2 to what power equals 2, right? That's just 1. So that's going to be 12. Why is it 12 notes? If middle C has a frequency, so they are now giving me the frequency of 261.63 hertz. How many notes above middle C is A4, which has a frequency of 440 hertz? So now they have given me my frequencies, correct? So now I'm plugging in something a little bit differently. They are still asking how many notes. Yes, how many notes? They're still asking that question, so we still don't know the N. 12 and log base 2 are given. We're not changing that. My higher frequency is 440. That's going to go on top. My lower frequency is 261.63. That's going to go on bottom. I'm a base 2, so I'm going to use my change of base formula to figure this out. You should do 12 times, we have log of this little guy here. You're going to put that in your calculator because I'm definitely not doing that in my head. Divided by log of 2. What do you get? So yeah, you should get 9 notes. That is 9 notes above C, by the way.